and click. Check it. I'm getting faster here, but this is my.
Hello.
Okay, now we have to. Okay, good. Okay, last talk and oopala, and then ask immediately. But first, Marcel and Ash.
Good afternoon, everyone, and welcome to our talk on explainable fingerprints. My name is Marcel, and before we start, just a little disclaimer that although Sanofi supports me being here and giving the talk today, all the work and all the results we present was completely done outside of Sanofi. So back to explainable fingerprints. What is this all about? Let's imagine you want to generate a machine learning model for predicting molecular properties. So you have a molecule data set, you generate some representations, so descriptors or fingerprints or graphs. Then you train a model with algorithm of your choice. And in the end, you get a property prediction. And what is interesting to know in this pipeline is, first of all, what information does the model actually get through the input representation, and what happens here inside of the model and drives the prediction. We will focus today on molecular fingerprints, especially on Morgan fingerprints. So as a little refresher for you, what are Morgan fingerprints? Morgan fingerprints are circular fingerprints that are that take the neighborhood of each atom with different radii into account, considers different properties of an atom, like the element, the degree, number of hydrogens, and it's very similar to the ECFP implementation in Pipeline Pilot. For the naming, so for Morgan you use the radius as the number behind the name, and for ECFP you use the diameter. So a Morgan 2 roughly is similar to the ECFP 4. It encodes the presence of unique substructure environments into single bits, and usually you fold it to a fixed bit vector length, which leads to collisions. We will talk about that later in more detail. What can you do with fingerprints? So you can do similarity calculations using different metrics like Tanimoto, like dice similarity, to get similarity value between two molecules. You can do a visualization of chemical space, where you bring down the Morgan fingerprint through dimension reduction methods to 2D space, for example. And you can, of course, do machine learning, where the bits then encode different substructures here. And what might be interesting to know is then which are the most important features for the given problem for the machine learning task. This question leads us directly to the topic of explainable AI. So what is explainable AI? Let's have another example. You have a molecule here, you have an HERC model, HERC prediction model, and you get a PIC50 out of it. And you are asking now, why is it telling you that? Is it because of this substructure, or maybe is it because of this substructure? This is something you would like to know then for the prediction. So with explainability, it is quite difficult, since for algorithms that get even better performance for prediction tasks, the explainability decreases usually. And what we would like to have is that the performance, of course, keeps at a high position, but you want to increase the explainability of these models. For explainability methods, there are many different approaches. One is the construction approach, where you try to introduce explainability methods or features while you are building the model. And the second one is that you use explanators, for example, with an already trained model, where you want to, for example, mutate input representations to see how the model behaves and try to get the importance of the single bits. So why is this explainable AI method so important? Let's illustrate this with a little example. We have here a little image of a horse. This is part of a very big training set for a convolutional neural network, which is just predicts if an image contains a horse or a cat or a dog. And this model was always predicting that this image contains a horse, which is obviously correct. But when you look into this model, then what drives the prediction for this classification, you actually see that the important part of the image is not the horse, but the copyright tag at the bottom left. This is why it is important not only that the model is correct, but also to know why the model takes actually the prediction. Using Morgan fingerprints in the context of explainable AI can be quite challenging. Let me explain why. Let's again have here one molecule. You then generate a Morgan fingerprint here, and then you train a model or you use a model for a prediction, and you get a prediction. And again, you want to know why it takes the prediction. So what you can do now is you use a known feature importance. For example, if you use a random forest, you get it like for free out of the model architecture. You can also use external tools like SHAP, for example, to generate this feature importance. Let's say you know that the bit number X is the most important one. So with this information, together with the fingerprint, together with the molecule, you can actually extract then the substructures that are encoded into this particular bit. You see here already that there are two different substructures encoded into one bit, which also is a visualization of a collision. But the question is, are these substructures really important for the task of the prediction? Let's have another scenario. You're not having one molecule, but you have many molecules. You have many Morgan fingerprints. And then you look into the substructure bit X again. And what you get then is the distribution of all substructures encoded into that particular bit for the whole data set. And you can see here, for example, there are not only these two substructures that are falling on this particular bit, there are actually four if you consider the whole data set. And if you look at the counts, so how often does the substructure occur in this data set, actually substructure C, which is not depicted here on the slide, seems to be the most relevant one for the model to take a prediction on this particular bit. To get a better insight on this and to try to make Morgan fingerprints in context of data sets a little bit more explainable, we want to introduce the tool XFP, which stands for Explainable Fingerprints, and is an open source model agnostic Python software to perform explainable machine learning on Morgan fingerprint-based models. You can extract and visualize Morgan fingerprints and substructures in the context of complete data sets. You can export substructures as smarts patterns to use it in other applications or tools, for example. You can also generate feature importances using different methods, for example, SHAP. And you can generate nice PDF reports that contain the importance of the bits, the substructures, and the distributions over the data set. It's available on GitHub since yesterday, actually. So to get a little bit more into the tool and explain what we actually do here, everything starts with the substructure calculation. So we have, again, our data set of molecules, and then using the get Morgan fingerprint as bitback function, which is actually contained in the allchem module, but how I import it, it's always chem. So you use that, and you actually get then the fingerprints, and you get the bit info dictionaries, which you can get provided if you provide an empty dictionary to the function. Together with this dictionary and this fingerprints, you can then use the find atom environment of radius n function to actually get then the substructures of all the molecules of all bits into our dataset. Then we can use the mole fragment to smiles function to actually convert them to unique canonical smarts patterns, which we can then do statistics on. So now we have our substructures here, but we still have the problem of bit collisions. And with that, I would hand over to Aishvarya, who will go into more detail on that.
So thank you, Marcel. Perfect. So let's talk about bit collision in more detail now. So one particular bit for one compound might end up encoding multiple substructures. This usually happens in the folding process of the Morgan fingerprint generation. And this type of bit collision is something we term as local bit collision. On the other hand, let's as Marcel told, like in our whole data set, we could see multiple substructures getting encoded as well in one bit. And this type of bit collision is something we term as global bit collision. In this small example over here, we have 3 compounds in our data set. For compound 1, we see a local bit collision, which is happening at bit number 5 over here. However, we also see that bit 0 over here might end up encoding multiple substructures, even for different, when we look at across the whole data set. To talk more about this, so local bit collision, or the bit collision as we know of, has been are quite rare, and this has been established quite well by numerous blogs by Greg. However, they also depends on the number of bits set by user. So the fewer the bits user set, the more chances of local bit collision to happen. Similarly with the global bit collision, they are unfortunately a lot more common. However, they also tend to increase with the lower the number of bits set by user, and also the diversity of the data set and the more compounds which are up if present in the data set. Which brings us to now an important question. We find bit 5 as the most important one, but which of the substructure which is encoded in here is the most important one, or let's say most relevant to our bioactivity in question? Possible answer is the most frequently encoded substructure over here. Now, changing gears to feature importance method of choices. There are numerous feature importance methods of choices available now, and most of them calculate feature importance differently. Thanks to the modularity of XFP, we allow advanced users to add their own feature importance method of choice in the XFP, so that their workflow is unhindered. As of now, we have included 2 different feature importance methods of choice. One of them is sharp tree explainer, and the other one is the inbuilt feature importance methods calculated by the XGBoost. For the rest of this presentation, we are going to stick with sharp tree explainer. So here's a super quick intro about it. So sharp tree explainer is a feature importance method just for the tree-based models. And this is based on a sharply game theory base for explainable AI. And what happens over here is input features for one sample get a score, which leads to which sums up towards like which side of the prediction, which class of the prediction is going for classification, and the score in general towards regression. And the higher the score each feature has, the more important it is. Here's an example of sharp summary plot of the tree explainer. We see the top 10 Morgan fingerprint bits over here illustrated by this plot. When the bits are switched on, since these are binary, the bits are shown in red color, the dots are shown in red color, and the negative sharp value, it indicates the impact of a particular bit towards the first class of the binary classification. And this class could be usually the inactive class or the 0th class, etc. On the other hand, like if the sharp value of bits are towards the positive, this would mean that the model outputs are impacted towards the second class, which is usually the active class or the first, like labeled as 1. But again, it depends from user to user. What we see over here in this example is that when the first bit, like over bit 807, is switched on, the model outputs are impacted towards the negative class. This would mean that the substructures which are encoded by this bit might be causing the activity in question, or let's say inactivity in question. And vice versa, as with the other 2 bits, we see when they are present, when they are switched on, which means the substructure encoded in them are present, they're causing the bioactivity in question. Any feature importance method of choice is incomplete without having easy to understand report by the end user. We considered this in the while designing XFP, and we allow advanced users to add the documentation manager of choice. However, the default documentation method of choice in XFP is a very intuitive PDF report, which I'll show you in the next slide. And the best part about this is that this report could be easily understood by cheminformaticians like us, but also by chemists. So here is how one page of a report is going to look like. It will be, let's go section by section. The first section will always have the feature importance method of choice, like plot for a particular bit in question. So over here, we see the sharp summary plot for this particular bit in question. And we see that when this bit is switched on, the model outputs are impacted towards the active class. The second part are the substructures encoded in this particular bit. And while visualizing these bits, an expert can link the activity in bioactivity in question with the substructures which are shown over here. Last but not the least, but rather one of the most important things we see now are the frequency tables now. So we see in this particular data set of 1,200 compounds, second column would comprise of the substructures, what are determined as accurate smarts patterns. The total occurrences, this would mean that since a substructure could occur multiple times in the same molecule, so this column would show the total occurrences, including the multiple occurrences. Unique occurrences would simply mean the total number of compounds encoding this substructure at least once. We didn't stop here. We also performed a validation case study. This was carried out by my master's student, Hannah, as part of her research internship. What we did over here was we gathered publicly available data from Campbell on very well-established targets in drug discovery, 5 of them. And we prepared a binary classification model on XGBoost. We also did some, we just selected the best model, which came out of hyperparameter tuning. And then we ran XFP on the best performing model on the test set for each target. And then we compared this top substructures, which were found as important in the XFP, or more like determined important by Hannah using XFP, and then comparing it with the literature data and seeing what comes up. One of such targets is HERG, and HERG is a very important, very well-established toxicity target in drug discovery because it codes for an important protein which if inhibited by small molecules, could cause severe arrhythmia. And that's why in drug discovery campaigns, any molecule which could trigger HERG liability are basically deprioritized. So what we found over here, so out of 10 bits, here's just an example over here. These 4 bits were found important, and these were the key substructures which were primarily encoded by these bits. And these were the bioactivities which we saw using from the sharp summary plot for each bit, like how the presence of bit is impacting the bioactivity either towards inactivity or activity. And we did find literature data which matches what we found in the XFP. So we should really have a preview over here. So this, we would just like to say that XFP doesn't link to bioactivity, but it's rather on the interpretation by the user and like how they interpret the results. XFP is just a visualizer, and it will help you understand what the substructures could be by important bits. So yes, is up to user how they understand, how they interpret it. With this, we come to the conclusion. We introduce XFP, and we really hope that it brings transparency in your machine learning models trained on the Morgan fingerprint bits. The code, as Marcel told, we pushed it online on publicly available on GitHub yesterday, and we will soon have a manuscript for it. A recommendation from us: we would like to emphasize that XFP should not only be run on the test set, but also on the training set, rather all validation sets. And this would allow user to interpret what are the substructures which might have been found important by the model during the training phase. And when we ran XFP on the test set, one could actually understand why their models were not performing well, probably simply because the substructure which was found important in the training set is simply missing in the test set. So this kind of clarity could be definitely useful to understand the model performances as well. What comes next now? This is just a start. We would like to introduce more feature importance methods of choice. Morgan fingerprints are, again, just the beginning. There are many fingerprints out there. We would also like to implement them in XFP. Last but not least, we would also like to have machine readable outputs, especially for the tasks like reinforced learning, to be performed when using XFP in collaboration projects. With this, we would like to thank a lot of people and who's been part of our journey, and especially right now all of you for your patience. And we open the floor to discussion. Thank you.
Questions, comments? You go last. No.
Thanks. So if you haven't done it yet, I would really strongly encourage you to look at the variability of your feature important measures with the data set split that you do. Because in my experience, if you're using a non-trivial data set, and HERG is pretty trivial, because there are key substructures that go along with it, so it's easy to tell the story. But if you do a non-trivial data set, in my experience, the variability of the most important features varies incredibly with the data set split, which leads to the obvious conclusion that what these methods tell you is what the model has learned from the data set split that you gave it, and it doesn't necessarily have anything to do with the underlying problem. So I would encourage you to take some non-trivial data sets, do the random splits, or do however different splits, and see how different the conclusions you get are. In my hands, I get 60% overlap between different random splits, which to me says these methods are not telling us anything useful if you have a non-trivial problem. And there should be a paper on this, but I'm bad at writing papers. So.
A comment?
We actually, since this was part of a research internship and we had limited time, we also wanted to test what important comes out of XFP. And we didn't want to have a whole research on establishing on a, like you said, rather unestablished target. So that's why we took the very well-established targets, because we have literature data readily available for them. So that was the goal of the validation study. But this is a very good point, I would say. However, again, the point comes to this, that XFP is more for understanding the fingerprints, which, let's say, in a best world scenario, the feature importance which comes are relevant. So this is a tool which could help.
You had a question?
We can agree to
Yeah.
disagree.
We have one more question, or at least one more.
Thanks very much for the nice presentation. I'm just curious whether the method assumes or relies on the bits of the fingerprints being independent, because given that neighboring atoms they influence each other's fingerprints. Does that have an effect on these shapely methods? So you can remove a hydroxy group, but the atom beside it, its fingerprints knew that there was an oxygen beside it, so that the bits aren't independent. So I'm just wondering, does the method assume independence of the features? Does that make sense?
Again, I would like to emphasize this point that it's a fingerprint agnostic, like it's a feature importance agnostic as well. So I can't comment much on how shapely would determine like which bits are important or not, but rather this is giving a platform for the developers, like for cheminformaticians, to actually interpret those values. What bits come out important on which data set, that's something we frankly don't care about. I mean, like just, but yeah.
Insufficient answer, but let's do it in a break now.
Yeah, I have one very short question. So at this stage, when you have a bit and it has important weight in the model and you do the vote, what's the most occurring substructure? Do you observe that some things that are just baseline, very common, like certain radius 0 on bits, can they pollute it? Like, for example, aliphatic CH2 or aromatic CH, isn't it possible that this can win the vote despite not being the relevant fragment?
Definitely, this is definitely also an issue. So at least for some of the targets, we did have the substructures at radius 0, which frankly don't make any sense. So that's why, like we've been emphasizing, that it's up to the end user how to interpret those and use their chemist intuition as well. Okay.
Yeah, so I mean, you showed the HERG data set, right? There is a substructure bit with radius 0 that'll work great on HERG. So you can't say that the substructure with radius 0 doesn't have any meaning, right? The nitrogen, the basic nitrogen, which you can get from the MFP0 bit, is more than sufficient to give you a very good HERG predictor on normal data sets.
Definitely.
So you just said that you can't have an MFP0 bit be important, and that's a case where the MFP0 bit actually determines what happens in that system. So I think you need to be careful about that.
So just on this example over here, again, chemistry is not my strong suit, but this happened in this particular feature importance plot. Yeah. So over here we see like tertiary amine and the piperidine derivative. They show exactly how it matches with the literature data. They cause HERG toxicity. However, Hannah also found a base like radius 0 nitrogen showing the other way around.
It depends on which radius 0 nitrogen.
Yeah, but like we are just looking the top 10 bits which came out for this analysis. So this could definitely be, I agree. So that's why we emphasize that chemists, so this is just a report, and how they infer it is up to the expert now.
More questions? I mean, at least I've seen one comment from Nick, but I mean, for the sake of time saving, we should move over to be on schedule. What do you think, Greg? Yeah. Whatever. I mean, you're the host. I mean, I'm moderating. Yeah, okay, good. So then, I mean, just a recommendation also from Nick. I would suggest structures on sample molecules on active or inscribed, depending on the SHAP value of the bit. Yeah, maybe I can show you who Nick is. And then there was from Jimmy. Yeah, I'm also here, right? You want to say something? Oh. when you have a substructure match, I say like this is a substructure that is active in your fingerprint analysis. Is there a way to, if the compound has multiple of substructure, is there a way to find which one of them was most important?
Maybe you can handle this question.
Which occurrence of the substructure? If you have multiple occurrences of the same substructure in the molecule, how do you know which one is the important one? We can. So there is nothing important to this particular bit. So we only know that it is there.
We can actually get then also where it is, but which one in this case, this is not encoded into the fingerprint then.
Let's thank Marcel and Ash.